All right, for the last question, I will use the solution. So let's read it together. So I have a martingale, which is a geometric Brownian motion, so it's a specific form of a martingale. And I have a stopping time tau, which is at the time where my Brownian motion is bigger than 1 or smaller than -1. So the first time my Brownian motion exits the strip. And I want to show that the expectation of tau is equal to 1. So we already computed that, but we're going to find out a different way using geometric Brownian motion. We did that using the square of Brownian motion. So first of all, first question is to argue briefly that the expectation of m at time tau is 1. And the second question, I can compute the moment generating function of tau with a certain parameter sigma squared over 2, and it has this form. And not surprisingly, once you have the tau, the moment generating function, you can evaluate it at a specific point. So actually you take here sigma is equal to the square root of 2a. And for that, if you plug that in there, you get e to the minus 8 tau. When you take the derivative, the tau gets out, and you validate a equals to 0. So you get the expectation of tau is the derivative of what you computed there with respect to a for sigma equals the square root of 2a. Okay, and you get that. So let's go through it point by point. So first of all, how do I know the expectation of m tau is 1? Well, we apply a Doob optional stopping. So remember that for martingale, you always have that the average is constant. In that case, at 1, position at 1 at time 0 is actually 1. It's not 0 because it's exponential. Alright, and Doob tells you can do that also for stopping time if you have two conditions. So optional stopping, you need two conditions. Tau is finite, almost surely for every pass, and also that the stop martingale is bounded. I should say bounded. It's smaller than infinity, but bounded. But you have that here. Just look at the picture. We know that Brownian motion have to get out of a strip. We did that in class, and it's stuck between the strips. So before it stops, it's always cannot take large value. So I can apply Doob here, and I get this. Now, how do you go next steps? So now I know that 1 is equal to this, and now we're going to play with this right side. And the way to do it is use the hint, that is, you condition on either beta is equal to +1 or beta is equal to -1. Now, if beta is equal to +1, you get e sigma here, and -1 you get e to the minus sigma. Now, the trick is to realize that Brownian motion is symmetric, so hitting +1 or -1 is 1/2. Get 1/2, 1/2. Okay, and the last step is to realize that the expectation of this guy given beta is equal to +1 and the other condition, they must be equal. So to see this, just redo the same conditioning but without the b. Okay, so write this expectation as this expectation given beta equal to +1 and given that beta is equal to -1, and because priority is 1/2, 1/2, you're going to get that this is equal to that. Okay, or you could just argue by symmetry. Okay, so what you get at the end, and I wrote it here, is 1 is equal to this factor, and you get the factor e sigma e to the minus sigma divided by 2. Alright, so we have that the moment generating function of tau with this parameter minus sigma squared over 2 is 2 over e sigma plus e to the minus sigma. Now it remains to just differentiate. Again, you have to differentiate with sigma equals square root of 2a, differentiate with respect to a. Be careful with your derivative, and then you evaluate at a equal to 0, and you get 1. Okay, exactly as it was suggested here. All right, so that's question 4.